Well, welcome to RamZland. I'm so glad that you were able to come to our show today. What I want to show you guys today are a lot of examples that demonstrate heat transfer. There's three kinds of heat transfer that I want to teach you today. And if you've ever had a pot of boiling water on your stovetop, then you probably held the handle of the pot of water and felt heat from the handle. That's called conduction. That's when heat travels from a solid to a solid. So if your mom says, don't touch the top of the stove when it's on, and you touch it and you burn your finger, that's conduction. Now the second kind that I want to show you today is called convection. So if you have water that's boiling in your pot on the stove top and you put your hand over the top and you can feel steam coming off, that's called convection. Or if you touch a warm liquid, like if you're in the bathtub and you turn the hot water on and it slowly heats up all the water in the tub, that's called convection too. So that's through a liquid or a gas. And then the third kind is, of course, radiation. So if you've ever built a campfire and you're several feet away, but you can feel heat coming off the fire, that's called radiation. Or if you're outside and you look up at the sun and you just feel heat against your cheeks, that's called radiation too. That's heat transfer through electromagnetic waves. And so three kinds today: conduction, that's solid to solid; convection, that's through a liquid or a gas; and the last one, radiation, that's heat transfer through electrons. And so for this first demonstration, I like to call this flaming hands. I hope you like it. Okay, so let's try flaming hands. All I'm going to use is a little bit of methane, and I put some water in here that has some soap mixed in it. And the first thing I'm going to do is I'm going to get my hands wet, and some of that heat is going to transfer to the water on my skin. That's convection. And then a lot of that heat is going to convect away from my hand. So when you see the fire, notice that the flame is rising. Hot air rises. And so as long as I don't have most of the bubbles underneath my hand, all that heat is convecting away from my skin. So I'm going to make some bubbles here. And I'm going to scoop some up with my hand. And watch what happens. Flaming hands. Look at that. And I don't feel any heat on my hand because it's convecting away from my skin. That's through a gas or a liquid. Now some of the water on my hand warmed up too instead of my skin, so that protected me too. So just a few bubbles. Notice it's on the top of my hand, not under my hand. I get close to the flame and look at that. Isn't that amazing? And some of you may have seen that I closed my hand. So if I close my hand, then I'm depriving the methane from oxygen, because fire needs oxygen, heat, and fuel to burn. So if I just close my hand, that puts the fire out. Watch one more time. Here's some more bubbles. Watch me when I close my hand. I'm going to close my hand and it goes out. You see that? I call that flaming hand. So the fire, that's radiant heat. When some of that water on my hand warms up, that's convection. When the heat rises off my hand, that's called convection too. A lot of people, when they see a water balloon over an open flame, they think that it will burst. So all I'm going to do is just pour a little bit of water into a balloon that's attached to my funnel. And this really demonstrates a lot. It demonstrates convection, it demonstrates radiation, and conduction too, because the little O-ring that the balloon will sit on, that'll get hot. And this is a solid, the O-ring's a solid, so that really demonstrates conduction. So once you have a little bit of water in there, then just inflate it the rest of the way. And you can shake it around. I can see some water in there. Yeah, there's some water in there. Now I'm going to tighten a knot. And we want to do a couple tests here just to make sure that I'm not using any tricks. So I'm going to take another balloon and I'm just going to put it over this same burner, but this one won't have water in it. How long do you think this balloon will take until the radiant heat from a flame will make it pop? How long? Maybe a second or two? A minute? This can be an open flame for a minute and not pop? Well, let's test your theory.
10 seconds?
Okay. So here's our burner. Okay, so this balloon has no water in it, okay? I can feel heat coming off the flame. That's called radiation. This little metal O-ring, it's pretty close to that flame, so I think it's heating up. If I touch that O-ring right now, that would be conduction. So I'm going to put the balloon over it. 1,000, 2,000, maybe 2 seconds. Okay, so the next test will be with our water balloon, and it'll look something like this. Our burner, and let's not change any variables, so I'm going to leave it at the same height over the ring stand. The difference is this one has some water in it, okay? So let's see if it pops, or if that water transfers the heat away from the latex. So this latex is stretched, it's really thin, so it's pretty easy to pop latex. But as long as some of that heat can move to the water through what? Convection, then the water heats up instead of the balloon, and it doesn't pop. Now that O-ring is getting hot too, so that's solid to solid, that's called conduction. And of course I can feel heat from the flame, and that's called radiation. Good. Okay, so next demonstration that I think really shows the difference between conduction, convection, and radiation has to do with our matchstick, its center of mass, and what happens when you light one end of the matchstick. Okay, so it looks like you got your fork and your spoon balanced on a matchstick that's balanced on the edge of a glass. Yeah. What do you think is going to happen if I light the end of it on fire?
I think it's going to stay balanced. Yeah.
Okay, let's see. And it stays on there and falls over. Kaylee says it'll stay balanced.
The stick is burning. It's falling down.
Still burning. Oh, you can see the end of it curl. Still burning.
There's ashes on it.
Oh, look at that. It is just barely on there.
It burned.
And it did burn past the edge of the glass, and it still stayed on there. That is just amazing. So we know that heat transferred through conduction. The matchstick is solid, the glass is solid, but since the glass is bigger, all the heat went to the glass, and there wasn't enough heat to keep that fire going. Okay, so what do you guys think will happen if I light one end on fire? Do you think it'll fall over?
No. It'll stay
Okay,
down.
let's find out. See it burning.
It's definitely having trouble.
It's having trouble. The flame is radiating heat, but it's also, the stick is conducting that heat to the glass. So since the glass has more mass than the matchstick, all the heat goes to the glass and the fire goes out. Isn't that something? Crazy. Okay, so for this next demonstration, it's a great way to show the effect of convection through radiation. So all I'm using for this is a pipe that has got a wire mesh inside of it. Kind of hard to see. I call this my singing tube. And I'm going to use a blowtorch to heat up that wire mesh inside until it's red hot. So the blowtorch is radiant heat, that's fire. But when that metal mesh gets really warm in here, that's going to heat up all the air inside the pipe. So when I tilt the pipe upward, what does hot air want to do? It convects upward. And if you have hot air rising inside of a tube, think of a pipe organ that can make a resonating frequency if you have enough air traveling through a tube. The thing I'm going to do a little bit different is I'm going to hold it sideways. So when it's sideways, you won't hear anything, but when I tilt it, that's when that hot air will start to rise. Right now, I'm just heating up that mesh inside. Okay, watch. Isn't that ridiculous? Just the basics. I'm going to heat it up again. Notice when it's sideways, what am I preventing? Hot air from rising. Okay, but if I just tilt it a little bit and that air can rise, then you get that resonating frequency. So again, I'm just heating it up. You can kind of see it glowing inside. So here we go. That's my singing too. You can try it home. And we'll set this up at each of your tables. But all you need for this is just a Coke bottle, or really any bottle that has a mouth that matches the same diameter as your coin. So if you use like a Mott's juice bottle, you might want to do this with a quarter. If you use like a pop bottle like I do, a penny fits it just perfectly. I'm also going to put some ice cubes in trays on your table because you want to cool the air inside the pop bottle before you touch it with your hands. When you touch it with your hands, that's conduction. Your hand is solid, the bottle is solid. But when the air inside starts to rise and it hits the penny, that's convection. That's hot air rising. Okay, so I see you got the penny on top. Did you drizzle some water on it?
Yeah.
That's a good seal. Okay, go ahead and grab it. Now let's see if that penny moves. Keep watching.
Squeeze it harder.
Keep watching.
I see it bubbling a bit though.
Oh, it's gonna move.
I see.
There it goes. I saw it click. Ah, isn't that crazy?
I'm gonna get a bit more heat on my hands.
Lots of water. More on that. Okay, good.
The first time.
Okay, now when you grab it slowly and squeeze it without bumping the penny because you don't want to ruin that seal that you got. Good. Okay. Watch the penny. Oh, I saw it move.
You got warm hands.
Oh, it's gonna move. There it goes. You got it. Good job. That's hot air rising in the bottle. That's called convection.
Yeah, for some reason a lot. I don't know why.
That's good. Okay. All right, now when you grab it, don't bump the penny when you grab it. Grab it with 2 hands. Go ahead. Good. Okay, and watch the penny.
Okay, don't squeeze it hard. Just hold it.
Watch that penny. Oh, there it goes.
You
You see it? It's moving. There it clicked. Yeah, you got it. You got it. You're doing it right.
Nice.
I like to call this next demonstration the Frankenstein's fire vortex. Now, when you see a fire vortex, I want you to think about what's happening because this does happen in nature. We know that hot air rises through convection. We know that fire needs oxygen. So as long as you have a lot of air that's rising in a forest fire, if that hits a jet stream and it starts to rotate, the fire is going to follow the oxygen. So this can happen in nature. Safety. And remember, when I start to rotate this, that angular momentum is going to draw air in through the sides of the basket. The basket's vented, and the fire is going to follow the oxygen. Fire needs oxygen for combustion. All right, so let's see if we can get it started. There we go. Okay, now right now nothing's happening because I'm not turning the basket. So it's just drawing oxygen through the top, okay? But if I start to turn it, look at what that angular momentum does. It creates a vortex. Isn't that amazing? And when I'm ready to put it out, I just take the plunger and I just snuff the fire out. Okay, this next demonstration I could call my hairspray cannon. And hairspray, a lot of people don't know, is mostly ethanol. And when ethanol combusts, it breaks down into carbon dioxide and water. And we are going to fill the combustion chamber of this cannon with a little bit of hairspray. Now, I'm going to use our Ben Davis t-shirt here as our projectile. So when I put it down the barrel, there's a couple things to think about. If it's too tight, then the thermal expansion of the hairspray will build up too much pressure and the combustion chamber will explode. So you don't want it to be too tight. You want it to be able to come out pretty easily. But at the same time, you want it to be tight enough so none of the hairspray escapes out the end. So it's kind of, you want it to be tight but not too tight in there. So this is how rockets work, how cannons work. So if it was this way and the combustion chamber is up here, then the thrust would come down the barrel and cause it to rise, like a rocket. If it's this way, then it's working, the combustion chamber is working like a cannon would. And you have thermal expansion down here, launching your projectile inside. This one's kind of loud. So if you feel like you need to cover your ears, I'll show you a preview of it. So we've already got our shirt down the barrel. We're gonna put a little bit of hairspray. I wanna talk about this ignition switch. This is a piezoelectric switch that just creates a small spark like in your barbecue. It's the same kind of thing. And I'm gonna put that on the end of it, and that's gonna serve as our ignition for the hairspray, which is mostly ethanol. So I'm gonna screw our end on, Yeah, I'm gonna aim over here. Well, I'll aim for the back of the room. I think that would be interesting to see if we can. You guys think we can make it all the way to the back of the room?
Yeah.
All right, so this is loud. So if you want to cover your ears, we're gonna launch our shirt in 3, 2, 1. Oh, it made it to the back chair. Ah. This is the single displacement reaction between potassium metal and water. And potassium is just an amazing metal. It's very silvery, it's very soft. And when you put it in water, it reacts with water to create potassium hydroxide and hydrogen gas. And so what I'm going to do is I'm going to have, I think, a little bit of potassium out here. Right now it's in my mineral oil because potassium reacts with water, and so you want to store it in mineral oil. I'm going to take out a few pieces here so you really get a chance to see this up close because it's just amazing.
It smells.
And all we're going to do is put it in water and it'll burst into flames. So, okay, so I have a little bit of water here. Now, again, when the potassium and water come together, this is a single displacement reaction. It displaces hydrogen gas, but it creates potassium hydroxide, and potassium hydroxide is alkaline. So I'm going to use a little bit of phenolphthalein. I'm going to put it in water. I see no color change. But after the reaction, when I add it to my potassium hydroxide, you'll see it turn kind of purple, pink purplish. Okay? All right, so are you ready? Potassium and water, here we go.
Whoa.
Isn't that amazing? What we want to do is add a little bit of phenolphthalein and see if it turns to that pink color. Are you ready? Watch. Watch. Look at that.
Pink.
Isn't that amazing?
Yes.
So we know that it's alkaline because it created potassium hydroxide. Whenever you increase the air pressure inside of a bottle, Charles' law says that if you increase air pressure, you increase the temperature. And a lot of people don't realize that if you just increase the pressure inside a bottle, it actually gets hotter as you increase the pressure. And so what I've got here are some bottles that have some air pumps on top, and these are called soda pop fizz keepers. If you want to get these on Amazon, they're very easy to release. You just pop the valve. And when I squeeze the top, I'm building up pressure inside the bottle. Now some of these I put a little temperature strip so you can see the temperature increase as you squeeze the top. You can release that pressure just by pressing on the end of it. Now I like to call these fog bottles because a lot of kids don't know what creates fog or clouds, and this is caused by any kind of pollution or pollen in the air or any kind of soot in the air that attaches to water molecules. So these are called condensation nuclei, and it could just be dust in the air. But if a water molecule can attach to that dust in the air, and you have enough of them, that creates fog or clouds, and that's what I want you to try out with these cloud bottles. Again, this illustrates not just convection, but the bottle itself actually warms up, which creates radiation. So when you release it, all you have to do is close it again. Don't let the isopropyl alcohol come out because that serves as the condensation nuclei. Those propanol vapors gives the water something to attach to. So just close it again when you're done, and then roll it around so you can see that propanol starting to vaporize inside. And if you're using this big bottle, you got to pump it about 30 or 40 times until it's tight. If you're using the 1 liter bottles, about 20 times, and it'll get really tight. You can look at your temperature gauge if you have a temperature gauge in there, and you'll see the temperature climb probably about 5 degrees Fahrenheit after about 20 pumps. And then to release it, you're just pressing down on this valve. So again, I'm just rotating it around. And honestly, when it's too hard to press the pump, that's when you're ready to release the vapors, the cloud bottle. Okay, so this is getting pretty tight. So all I'm going to do is just pop the lid by just pressing on it. And I have all that cloud in there. Isn't that amazing? And those are the water molecules attaching to the propanol vapors, this condensation nuclei. So when you're ready to start again, just close it. And then just start pumping, and it'll turn clear again pretty quickly. And you're ready to try it. Okay, so Aiden has increased the pressure in the bottle. You ready to pop the lid?
Yeah.
All right. There you go. Look at that. Isn't that amazing?
Wow. That was
You can
better
see
than
it coming
when I
out of
tried
there.
it.
Yeah. And all you have to do is just close. And we're ready to try our cloud bottle. Okay, pop the lid. Look at that. That is awesome. All right, so you've been pumping the pressure up in there. You have a little bit of isopropyl alcohol. Okay, we're ready. Look at that. Isn't that amazing? Okay, and you've pumped it several times? All right, give it a try. Oh, look at that. That is awesome. This is another exothermic reaction. A lot of you have been told to drink your milk because you need calcium in your diet to build healthy bones and healthy teeth, but a lot of people don't realize that calcium is a metal. And when I add calcium to water, there's a single displacement reaction where the calcium and the H2O, the water, create hydrogen gas. It displaces hydrogen gas and, of course, calcium hydroxide, and that's the equation that you see behind me there. So I'm going to have another flask over here. Well, I'm going to use my graduated cylinder, and we're going to add some calcium to it. Now, as I do this, I think what I'm going to do is I'm going to have another flask over here. I'm going to add some phenolphthalein as an indicator. Now, phenolphthalein is interesting because it only changes color in the presence of anything that's alkaline, a base. So in the presence of pH 7, which is pure water or an acid, it's clear. So you shouldn't see any color change when I add this. It should just be clear. I'm going to swish it around in there, mixing up our phenolphthalein solution, okay? Okay, and then in this flask, I'm going to add a little bit of calcium metal. And the gas that you'll see coming out, that's hydrogen gas. And intermittently, I'll ignite it with my lighter because we know that hydrogen is flammable and it'll make kind of a whoosh sound. And then at the end, we'll add our phenolphthalein and see if it changes color. I know how much heat is coming off this, how much radiant heat is coming off. So right now, we're going to do a test to see what the temperature is. So the temperature of the water right now is 69, I don't know if you can see that, 69 degrees, 69.6 degrees Fahrenheit. And when I start adding our calcium, it's going to immediately start to react and release that hydrogen, but it's going to get hot. So if the water gets hot, what kind of heat transfer is that? That's convection because it's a liquid. And if some of that hydrogen gas coming off of it, if that's hot, again, that's heat transfer through the gas, so that's convection too. But when I ignite the hydrogen gas, that's radiation, that's radiant heat. Okay, so I'm going to start adding our calcium. And you'll start to see it react. You can see it bubbling quite a bit. And if I ignite some of that, you can see it catch on fire. So you can imagine after not very long, I can take another shot of that. And it's already up to 82 degrees, 83 degrees, up to 86. Now it's 118 degrees, 127. So a pretty strong reaction is taking place. You also notice that it's starting to turn milky. So just like your milk looks white, look at calcium hydroxide, very white, very milky, up to 115. Let's see if we can light some of that hydrogen again. May not be enough. I don't think I'm getting enough. Okay, so next thing I wanted to do is add our phenolphthalein. So right now, this has gone from pH neutral to an alkaline solution. So anything that has a pH of above 7, the potential for hydrogen is pure water. So anything between that's higher than 7 up to 14 is a pH that is alkaline, okay? So this turns pink in the presence of anything that's alkaline. Anything below 7 is acidic. So milk that has, milk is slightly acidic. It's probably like a 6.5. Your coffee that you drink is around 6.5. Lemon juice would be much more acidic. But watch the color change when I add our phenolphthalein. Instantly, look at that. It turns pink.
My favorite.
So I know my solution is alkaline. And that's the single displacement reaction of calcium and water. I hope you enjoyed that. Very exothermic. A lot of heat being displaced. Our plasma cannon. This one's a little noisy, so for those of you who are sensitive to noise, you might plug your ears for this. I'll play just a preview of it so you can kind of get an idea of how loud it is. But rockets use what's called a combustion chamber for thrust. And so I'm going to use this big water jug as my combustion chamber. And I'm going to use ethanol as the propellant, or I use propanol, isopropyl alcohol. I'm going to use propanol as the propellant. So I'm going to put a little bit of propanol in here, and it's going to start to evaporate. And it's going to build up gas pressure in here because instead of letting it escape, I'm going to use this little spongy toy, and I'm going to trap all that gas in there. So when I ignite it, this combustion chamber has what's called thermal expansion. And all that heat is going to try to expand in every direction and launch our little foam toy here. So and I'm going to shoot our foam skull that way so you guys get kind of a side view of the combustion chamber and all that thermal expansion that's going on. So again, this is our wireless transmitter. This is called an Uden coil. It's kind of like a Tesla coil, and it emits a little bit of plasma that's going to conduct from one screw to the other, and that plasma is going to ignite all the propanol vapors inside. So if you're worried about the noise, you might plug your ears. If you think you're okay, don't worry. I'm going to kind of aim for the door over there. Are you ready?
Yeah!
In 3, 2, 1. Oh! A lot of thrust there. A lot of thrust. This is called the genie in the bottle. I love this reaction. This is again with hydrogen peroxide, which its molecular composition is very close to water. So remember, water is H2O, and hydrogen peroxide is H2O2. And so I'm going to put this little pellet of manganese dioxide in here. And to start out with, it's not very hot. Like right now, my solution is 71 degrees Fahrenheit with my infrared thermometer. Okay. I'm going to walk around with this, but I'm going to wear my welding gloves because when I come around to you, you'll see that pure oxygen. I think it kind of smells like mildew. But I'll shoot it again with our infrared thermometer, and you'll see how hot the flask gets because, again, this is really hot. When you touch the glass, that would be conduction, heat transfer through a solid. But all of that oxygen coming out is very hot, and that's heat transfer through a gas, and that's called convection. So here is genie in the bottle. In 3, 2, 1. Look at all of that oxygen. It's just amazing. Module that I want you all to try. And this really demonstrates how convection changes air pressure. Daniel Bernoulli was a scientist who discovered that when you increase wind speed, you decrease pressure. And so if you have a lot of hot air rising in a column, that convection current actually decreases the air pressure inside that current of fast-moving air. Right now, you have 14.7 pounds of air pressure pressing against every part of your body. It's just always been there since the day you were born. And if you wave your hand in front of your face, you can feel that air pressure against your skin. But in a really strong updraft, you have less pressure. So I'm not going to blow sideways like this. You won't get any lift with the can. But if I blow down at an angle and I make a little bit of space between the can and the edge of the cup for that air to go in, then I'll reduce the air pressure in this space, causing lift and making the can rise. And so I'm going to try it with the bowl. All right, so I'm going to blow down and try to capture it in the bowl, just like that, okay? So I want to give you guys a chance to try this again. If you're blowing it into a tray, I think it's easier. You do the hard one. All right. One hard breath down. Yes, yeah, you got it. Closer. Okay, give it a shot. Yes, you got it. Yeah, you got it. This is a really interesting demonstration. This is used as the pigment for yellow paint, and a lot of painters in the 17 and 1800s used this experiment to make the yellow pigment for the paint that they use in their oil paintings. And this is an endothermic reaction. So an exothermic reaction is where you're radiating heat. Heat is coming off of the reaction. Endothermic reactions is when you absorb the heat around. So an endothermic process would be like ice melting. It absorbs the surrounding heat to melt the ice. Even your heartbeat is an endothermic process. An anglerfish illuminating its tentacle through bioluminescence is an endothermic process. It's lowering its body temperature. When a firefly lights its tail, that's an endothermic process. And so in this reaction, this is a double displacement precipitation reaction between an aqueous solution of potassium iodide and lead nitrate. Now, when I combine these two, there's a precipitate. And that's when you have an insoluble solid fall out of the solution. So I have two metal ions. I have lead over here and potassium over here. So they're going to trade places. That's why it's double displacement. So the lead nitrate becomes lead iodide, and the potassium iodide becomes potassium nitrate. Okay? So this is so watch as they trade places in this double displacement reaction. They both look fairly clear. This one with the lead nitrate is a little cloudy. I always know which one has a little bit of lead in it. But this one's pretty clear. This is the potassium iodide. And watch what happens when we combine them. Instantly it changes. Isn't that just amazing? And that precipitate is more dense, and it'll slowly start to fall out of the solution because it's an insoluble solid now that formed between those two liquids. Just amazing. And this was used as the pigment in a lot of the Renaissance paintings that you'd see. They would use these precipitate reactions to make the pigment for their oil paints. I'll add a little bit more. Just amazing. I'll just let that sit there for a bit. Okay, this next demonstration I like to call the ghost bottle. This is an amazing reaction, and it creates a lot of light. It's very hot. This creates a lot of radiation. If you've ever read the phrase fire and brimstone, brimstone is molten sulfur that's on fire. And that's what you'll see in this demonstration. And so we're going to get oxygen through decomposition of hydrogen peroxide. So hydrogen peroxide is a lot like water. Water is H2O. This is H2O2. So if I just leave the lid off of 3% hydrogen peroxide, slowly this will lose that extra oxygen atom and decompose into pure water. It might take a while, but I can increase the rate of that reaction by adding a catalyst. And the catalyst I'm going to use for this is potassium permanganate, KMNO4. And what this will do is just speed up the rate of decomposition. This will just make more oxygen come out at once because, again, this is a synthesis reaction. We want that oxygen to bond to the sulfur to make sulfur dioxide. So I'm going to add a little bit of the potassium permanganate, and then I'm going to cover it like this. I'm just going to leave it covered. And then we'll get the sulfur ready. I'll ask Aiden to turn out the lights. I hope you enjoy this. So here's our first step. I'm just going to add a little bit of our catalyst. I'm going to cover it. And that gets our oxygen-rich flask ready for the sulfur. Okay, this is the second step. Here's a little bit of sulfur. And Aiden, this is a good time to turn out the lights. And again, we're doing this on a flame-proof blanket. Sometimes I'll get little embers of molten sulfur that'll come off of this. And so that's why we're doing it on the blanket. Okay, so I've got a little bit of sulfur on there. Slowly warm that up. Sulfur has kind of a blue flame when it starts to burn. And now it's ready. And here we go. Look at that. Isn't that beautiful? Just awesome. You can really see that blue flame inside as it bonds with the oxygen. Just amazing. It's our ghost bottle. This is one that a lot of people like. This is a very messy reaction. People call this elephant toothpaste. And again, this reaction is used with hydrogen peroxide and some soap and some potassium iodide just to speed up the rate again of that reaction. A lot of people like to use food coloring in this. just to color all the foam. Here it comes.
Oh,
Stand this way a little bit because it's going to expand. Here it comes. This is called elephant toothpaste. Now, as it decomposes, you'll start to see steam come off of it, and you can actually hold your hand around it, and you can feel that radiation. You actually see steam. So the steam that you see is convection, but it's actually hotter, than it looks. So if I hit it with my infrared thermometer, it's reading 158 degrees. So it's actually, it's warmer than it looks. 149. Yeah, so that's elephant toothpaste. And again, the trash bags are to contain the reaction with potassium chlorate and sugar and a little bit of sulfuric acid. And again, this is a really strong decomposition combustion reaction. So you're going to see a fair amount of fire with this. And all I have is a homogeneous mixture of potassium chlorate, that's the oxidizer, and granulated sugar. And I cut these two crystals until they look the same. Then I'm going to use sulfuric acid. Now the acid is going to start the reaction, and the potassium chlorate is going to use the sugar as a fuel. So the sugar is what's oxidized in this reaction. And at the end of it, it just looks like carbon because sugar decomposes into carbon, carbon dioxide, and water. And so as this reacts, it smells like you were roasting marshmallows over a campfire. That's the same reaction because marshmallows are mostly sugar. So if you ever caught a marshmallow on fire and it turned all black, that's what this looks like at the end. That's what it smells like. So full extent of this. And again, all I'm using to start this reaction is just a drop of sulfuric acid that I have over here. And I need to turn this off. Turn that on afterwards. Okay, are you ready? Okay, this is our grand finale in 3, 2, 1. Here we go. Look at that. Isn't that amazing?
Light fire?
A lot of radiant heat there.
Hey, look up.
Okay, you turn the lights on. Well, guys, I hope you enjoyed our time in RamZland. And if you want to see any of these videos, any of these demonstrations again, you can find me on YouTube, RamZland. I'm on TikTok, I'm on Twitter, I'm on Facebook, I'm on Instagram, RamZland. There's over 600 science demonstrations that I have on my YouTube channel. I'd love if you subscribe and get your kids excited about science. I hope you guys have a great day, and I'll see you next time. Thank you. Thank you.